Now we are going to talk about the engineering materials in general because we covered that last lecture and show you a diagram of the classification of the materials, and today we are going to go in details about the different metals we are going to use. So materials we are going to use. So the most important properties we have for the metals are, that's in manufacturing. First, we're always looking for the high stiffness and strength. And it can be alloyed for high rigidity, strength, and the hardness. We're also looking for the toughness, which is the capacity to absorb the energy better than the other classes of the materials. Good electrical conductivity, where the metals again are good conductors, and also good thermal conductivity to conduct the heat better than the ceramic and the polymers. The forms of the metals in manufacturing, this can be a cast metal, which always is going to starting from casting. So I'm going to melt the ore, for example, mix it with some material and put it in the mold, and I'm going to have the cast shape. I have the rolled metal, where the metal has been worked or can be worked after the casting, like the rolled sheet. The powder metal, which is starting from very small fine powders for conversion into a parts using the better metrology techniques, which is depending on the pressurizing of the parts together with a mixture and adding the bonding material, then centering the part to make it stronger. Once again, the classification of the metal itself, which can be divided into ferrous, non-ferrous, and superalloys. The first metals are the one which contain, the base is going to be the iron, like the steel and the cast iron. On the other side, the non-ferrous one is going to be free of the ferrous in their components, like the other metals like the aluminum, magnesium, the copper, the nickel, the titanium, zinc, lead, etc. And the superalloy, which is going to be a mixture of, it's not the alloy actually a mixture of the base metal and the other metal, but in the case of the superalloy, 2 or 3 metals with no base metal. That's mean all of them is going to be less or equal to 50-degree maximum in the component of the alloys. So for the first metals, it's based on the iron, as we said earlier, and engineering the alloys are based on the iron and the carbon. And these alloys are divided into 2 major groups, which are the steel and the cast iron. And together they constitute approximately 85% of all the metal tonnage in the United States alone. The iron-carbon diagram is diagram phase very important, and this will depend on the temperature we're going to have, and this will give us a transformation from the solid to the liquid state. So you remember last lecture we talked about the BCC, the FCC, and the other terms. So we said that the BCC means the body-centered cubic, and the FCC is the face-centered cubic. So the phase of the iron-carbon steel in the at room temperature is known as alpha, or also going to be called the ferrite. So you can see that the bottom there, actually I cannot, you will not be able to see the mouse. So the lower part of the diagram is what we know as the alpha plus Fe3C, steel iron carbonate, or ferrous carbonate, and this will be the solid state. As I'm going to increase the temperature, I'm going to have it transition to the gamma, and this usually going to happen at 912 degrees. So the ferrite, which is the alpha phase, which is a BCC, is going to transform to gamma, and it's also called the austenites. And the shape of the crystal in this case is going to change to the FCC, which is the phased cubic centers. Center cubic. And as I'm going to continuously add the increase the temperature, and the moment I'm going to reach the 1394 degree, I'm going to change the phase to delta, which once again to return back to body-centered cubic. Okay, so and also you can see that in this diagram we're going to have a mixture between the solid, it continues to remain as a solid at A1, and by increasing temperature again to have the melting point to occur at 1539 degree for the pure iron metals, until again to have the pure liquid ferrous at the end. As you can see that this will depend also on the carbon percentage in the freon I have, on the iron metal I have. Now the steel is an alloy of the iron which containing from 0.02 and 2.1% of the carbon by weight. Now that means if I'm going to have 1 ton of steel, that means it's going to consist of 998 kilogram of iron and 2 kilogram of carbon. That's if I'm going to have the range of 0.02%. And it may also contain other alloying elements. Now we call this one alloy because the base metal is the iron. It's more than 90 degrees, for example. The steel alloys can be grouped into 4 categories. The first one is known as the plain carbon steels. The second one is the low alloy steels, and the third one is stainless steels, and the fourth one is the tool steels. The plain carbon steel is the carbon is the principal alloying element with only a small amount of other elements, which is something about 0.5% of the manganese is going to be noble percentage. Now, the strength of the plain carbon steel increases with the carbon content. As long as you're going to add more carbon above the 0.02, that means that the strength is going to increase. But the problem is that the ductility will be reduced, simply because the carbon is a brittle material. The high carbon steel can be heat treated from the martensite and making the steel very hard and strong. Okay, now this is highlighted one. So the heat treating of the martensite will increase the hardness and strength of the metal alloy. If I'm going to have low carbon steel, that means that the percentage of the carbon is less than 0.2%. And the application of that is the automobile sheet metal parts, the plate steel for the fabrications, the road rails. And for the medium carbon steels, which have a percentage of 0.2% and the 0.5% of the carbon, the application is the machinery components and the engine parts, such as the crankshaft and the connecting rods. And the last one is going to be what we call the high carbon steel, where the carbon percentage is going to be greater than 0.5%, up to 2.11. And the application for that is going to be the spring, the cutting tools, and the plates. The low alloy steels, which is a carbon alloys containing the additional alloying elements in amounts totaling less than 5% by weight. So the iron is going to remain as 95%, and all the other elements plus the carbon is not going to be more than 5% by weight. The mechanical property is going to be superior to the plain carbon steel for a given application. It's going to have higher strength, as we said, because the carbon is increasing, hot hardness, and wear resistance and toughness. The heat treatment is often going to be required to achieve these improved properties. The tool steels, which is a class of highly alloyed steels designed for the use in the industrial cutting tools, dies, and molds. And to perform in these applications, they must possess a high strength, high hardness, hot hardness, wear resistance, and toughness under the impact. And the tool steels are heat treated as well. The stainless steel, which is a very common thing in life, and this is a highly alloyed steel designed for corrosion resistance, strength, and ductility, but significantly is going to be more expensive than the plain carbon steel, or the low alloy steels, and difficult to work in manufacturing, because simply it's have higher strength. The principal alloying element in this case is going to be the chromium, and usually is going to be greater than 15% in the alloy component. And the chromium is going to form a thin impervious oxide film that protects the surface from the corrosion. The nickel is another alloying ingredient in certain stainless steel to increase the corrosion protection. The carbon usually is used to strengthen the hardness in the stainless steel, but high carbon content is going to reduce the corrosion protection, since the chromium and the carbide is going to forms to reduce the available free chromium, the chromium in the alloy. The sensed steel usually is classified according to the predominance phase presence in the ambient temperature, and this can be classified as the austenitic stainless steel, which typical composition is going to be 18% chromium and 8% of the nickel. For the ferritic stainless steel, which you have to have 15 to 20% of the chromium, low carbon, and no nickel. For the martensinic stainless steel, which you're going to have up to 18% of the chromium but no nickel and higher carbon content. The cast iron, which is an iron alloy containing from 1% to up to 4% of the carbon and from 1% to 3% of the silicon. So you saw that the high carbon steel had up to 2.1, and if I'm going to have more than that, is going to be a cast iron. In addition to the percent of the silicon, we're up to 3%. And actually, I'm going to show you some fractured part in the lab, and you will show you will see that the crystalline shape of the material will show that the percent of the carbon and the silicon within. This composition make it very high suitable for as a casting metals, and the tonnage of the cast iron casting is several times than that of all the other cast metals parts combined, excluding of course the cast ingots in the steel making that are going to successfully rolled into our bars, plates, and the similar stocks. So just remember, you cannot make a bars or shaft by using the cast iron. The overall tonnage of the cast iron is second only to the steel among all the metals. Types of the cast iron we have: gray cast iron, the ductile cast iron, the white cast iron, the millable iron, and the various alloy cast irons. Usually the most common one is what we know as the gray cast iron. The non-ferrous metals on the other side, we said that although they are not, we said that these are the metals which doesn't have the ferrous, or the iron within their components. So although they are not strong at the steel, but certain non-ferrous alloys have the strength to weight ratio, which is make them competitive with the steel in some application. Many of the non-ferrous metals have the properties other than the mechanical that make them ideal for the application in which the steel will not be suitable. Okay, lightweight of the aluminum, for example, is very attractive, especially when going to make aircraft, as we said, in the manufacturing of the aircrafts, as well as if we are going to talk about the aluminum for the heat dissipation components. So the aluminum is a light metal, often specified in the engineering application for these features. It has high electrical and thermal conductivity, corrosion resistance to the formation of a hard thin oxide surface film, very ductile metals, noted for its formability, and has low strength when it's going to be pure, but it's going to be alloyed and heat treated to compete with some of the steels in the case of the strength, especially when the weight is going to be taken into consideration, because it's going to go for the aluminum over the steel. The other metal is the magnesium and its alloys. Now, the magnesium is the lightest of the structural metals, available in both wrought and cast forms, relatively easy to machine, and in all processing of the magnesium, the small parts oxidize rapidly and present the fire hazard. That means if I'm going to do the cutting on the magnesium part, the chip which is going to be generated, it's have the possibility to be oxidized due to the heat and the presence of the oxygen, and this will cause the fire hazard to present. As a pure metals, it is soft and lack of the sufficient strength for most of the engineering application. When it's going to be alloyed and heat treated, it's going to achieve strength comparable to the aluminum alloys. And the strength to the weight ratio is an advantage in the aircraft and the missile components. The copper, which is one of the oldest metals known to the mankind. It have low electrical resistivity, excellent thermal conductor, and corrosion resistance. The strength and the hardness of the copper is relatively low, and to improve that, the strength, the copper frequently is going to be alloyed. So we either going to mix it with the tin, with up to 10% of the tin, and we are going to have the ingot, which is called the bronze. The bronze is the alloy of the copper and tin, which is widely used, and actually it was one of the widely used alloy in the history, and we even have what we call the Bronze Age, where all the tools, where all the weapons were made out of bronze. The other one is the brass, which is an alloy of the copper and zinc, and this typically is going to have 65% of the copper and up to 35% of zinc. This one, the highest strength alloy is going to be the premium copper. We're only going to add 2% of the premium, and this will be heat treated to have a high strength and used for the manufacturing of the springs. The nickel ends alloy, and it's similar to the iron, when we're going to have the same modulus of elasticity for the iron, the 240 gigapascal for the modulus of elasticity, and have the same magnetic properties. It's different from the steel, as much more corrosion resistance, and have a high temperature properties of the nickel alloys are going to be superior. The alloys of the nickels are commercially important and are noted for the corrosion resistance and high temperature performance, and in addition, the number of the super alloys are usually based on the nickel. And yes, so we also have the titanium and its alloys, which is a very precious metal consisting only less than 1% of the Earth's crust. The density of the titanium is between the aluminum and the iron, with a lightweight and good strength to weight ratio, and have a lower coefficient of thermal expansion among the metals, and retain a good strength at elevated temperatures. At room temperature, the titanium forms a thin adherent oxide coating, and which is the titanium oxide, that's going to provide the excellent corrosion resistance that applies in the marine components and the other prosthetic implants, which is the part we use in biomedical. The titanium alloys are used as a high strength component at a temperature ranging up to above 550 degrees, especially where its excellent strength to the weight ratio is exploited. Alloying elements used within the titanium include the aluminum, the manganese, tin, and the vanadium. And the pure titanium is reactive, which will present a problem in processing, especially in the molten state. The zinc and its alloy have a low melting points, make it attractive as a casting metals, especially in the die casting. It's also provide a corrosion protection when it's going to be coated onto steel or iron. The term galvanized steel is refers to the steel coated with the zinc, and it's widely used alloy with a copper to make the brass. The super alloys is high performance alloys designed to meet the demanding requirements for the strength and the resistance to the surface degradations at a high surface temperatures. And many of the super alloys contain a substantial amount of 3 or more metals, rather than consisting of one base metal plus alloying elements as we had in the other alloys. They're commercially important because they are very expensive, and technologically important because because of their unique properties. The high temperature performance is excellent. The tensile strength, the hot hardness, the creep resistance, and the corrosion resistance at very elevated temperatures, which can reach the operating temperatures of often 1100 centigrade. The application we can have is the gas turbines, the jet and rocket engine, the steam turbine, and nuclear power plants, where the system is going to be operated eventually at a higher temperature. We have three groups of the superalloys, which are first the iron-based alloys, or the nickel-based alloys, or the cobalt-based alloys. It depends on the percentage of the in the iron-based alloy, we are going to have the iron more than 50% of the alloy itself. In nickel-based, we are going to have it's going to have a better high temperature strength, and then the alloy steels. And in the case of the cobalt-based alloys, we are going to have 40% of the cobalt and 20% of the chromium are going to be alloyed together with the nickel and the other tungsten and the other things. Virtually all the superalloys strengthened by the precipitation hardening. The ceramic is an inorganic compound consisting of metals and one or more non-metals material. And important examples of the ceramics are the silica, which is the silicon dioxide, which is the main integrated mode of the glass product. The alumina, which is the aluminium oxide, which is used in various applications from the abrasive to the artificial bones. And we have the hard US aluminium silicate, which is the main ingredient, is going to be most of the clay product. It have high hardness, electrical and thermal insulation, good chemical stability, and high melting temperatures. But they are brittle, virtually no ductility at all. And this can cause a problem in both the processing and performance of the ceramic products. Some of these ceramics are translucent like the window glass based on the silica, which being the clearest example. We have three basic categories of the ceramic, which are the traditional ceramic like the clay product like the pottery, the china, the bricks, the common abrasive, and the cement. The new ceramic, which are more recently developed ceramic based on the oxides, the carbides, and extra, with a better mechanical or physical properties than the traditional ceramics. And we have the glasses, which is based primarily on the silica, as we said earlier, and is distinguished by their non-crystalline structure, and that's what they make them transparent. The polymers is a compound or consisting of a long chain of the molecules, and each molecule made up of the repeating units of the that connected together. They may be by thousands and even by millions of the units in a single polymer molecule. And most polymers are based on the carbon, and therefore is considered to be an organic chemicals. As an engineering material, it has appropriately divided them to following three categories. First one is the thermoplastic polymers, which known as the plastic. Everything we have around us, we know it as the plastic in general, are actually a thermoplastic polymers. So the case of the computer you're watching this video on, or the TV, or the pen you hold in your hand, it was going to be a plastic one. The plastic cups and everything else is going to be made out of the thermoplastic polymers. So thermoplastic polymers are the one that you can melt it, shape it, then you can remelt it and reshape it once again. On the other side, if I'm going to have the epoxy, for example, I'm going to mix it to epoxy, for example, I'm going to have two epoxy to be mixed together, or even the glue. I can put it on the surface, I can leave it to solidify, I can add the heat to accelerate this process, and at the end it's going to be solidified. When it's going to be solidified, I cannot remelt it once again and use it. So that's what we call thermosetting polymers. The last type is the elastomers, and as you can see, this one is being defined by the rubbers. This can be natural rubber, and this can be petrochemical rubbers. So the rubbers properties are going to have higher elasticity rates. Okay, and of course the still have some limitation on the recycling, but the elastomers have different properties from thermosetting.